When we think about the density of the air molecules, we see that they are more spread out and less dense the farther we go up in the sky. They are closer together down here and more spread out up here. And of course, this is not to scale at all, just the best I can do with a drawing. And if we think about it, it makes sense that they would be packed together more tightly down near the Earth's surface because the weight of all the gas molecules above is being pulled by gravity towards the Earth and compressing them. However, a stationary picture, a picture like this rather than a video where they're moving around, doesn't fully express what is happening because we know that the gas molecules are continually moving. And we know that they're moving in all directions. Okay, so these are my gas molecule movements. So since they're moving in every direction, they're exerting pressure in every direction. They're exerting pressure in that direction against whatever is there. And I mean, they're pushing against other air molecules also, exerting pressure against the ground. But we can also realize that they're exerting pressure against the molecules above them because they're pushing up on those. So the way that I think about it is the gas molecules at sea level have to be exerting 1 atmosphere of pressure in the upwards direction to keep all these gas molecules from being pulled down to the Earth by the force of gravity. Okay, so now we're going to think about one aspect of the fascinating chemistry of this giant beach ball. Okay, so I really liked this picture. I think it shows us that we have a bunch of different gas molecules. They're moving, and so the arrow is showing the direction they're moving. We know they hit the sides of the container, and the gas particles are moving in all kinds of different directions, but on all sides, they are hitting the sides of the container. And so if we add up the forces of all those hits on the container and then divide it by the area, we get the pressure, and we know the pressure is being exerted in every direction all the way around. And we're thinking about that giant beach ball that I just showed you, just because I liked that picture. But even in a small ball, there would be many thousands of billions of collisions each second. Okay, so if we were thinking about the giant ball or the small one, the number of collisions occurring with the wall is unimaginable to me. And the force of impact of one single collision is too small to be sensed. But when we look at all of these together, the force of those collisions adds up to equal the pressure. And if you remember, pressure equals force over area. So the sum of the thousands of billions of collisions equals the force in total, and then divided by the area of that container that it's in, that gives us the pressure. So we've just looked at the pressure being exerted inside the ball. And now this picture is looking at what's going on outside of the ball. Okay, so outside of the ball we have all the air molecules, and again, air molecules are flying in all these different directions, but we are only concentrating right now on the ones that are hitting the ball. And these air molecules are all hitting the ball, and each collision involves force. We add up all the forces, divide it by the area. But the overall effect is that there is pressure being exerted on the ball from the outside. And what they have tried to show is that the arrows representing the pressure are equal for what's happening from the outside compared to what was happening from the inside. Okay, so this is just my attempt to show that in one picture. The force of these collisions causing the pressure on the inside. The pressure on the inside is equal to the pressure being exerted on the outside of the ball. So what would happen if we take out some air? If we take out some air, there would be fewer gas molecules inside the ball. If there were fewer gas molecules inside the ball, there would be fewer collisions with the walls of the ball. So what would we expect to happen? Okay, sorry about the scribble. I just wrote the wrong equation initially. So we know that the pressure is equal to the total sum of all the forces, which would come from all the hits of the air molecules in here with the wall. Okay, so that one exerts a force, this hit exerts a force, this hit exerts a force. So if we have fewer air molecules in here, then our force would be smaller. But we know that for this ball situation, the pressure of the gas molecules inside is going to be equal to the pressure from the gas molecules outside, because in this situation the ball can shrink or expand as needed to keep these pressures balanced. When we have two things in contact with each other, the pressures of each one, they're going to balance each other out. So fewer gas molecules inside, my force is smaller, therefore what has to happen is my area has to be smaller also, so that this quantity will keep the same pressure. The pressure has to stay the same as atmospheric pressure. And in order to make this area smaller, to go along with the decrease in the force, the volume of this gets a little bit smaller. So when we let a few gas molecules out of the balloon, we deflate it a little bit. The force goes down, therefore the area has to go down, and it shrinks, the volume decreases until the pressure inside is balanced by atmospheric pressure. Okay, so go ahead and think about this a little bit, and then answer questions 5 and 6 on the pressure section of your lecture notes. See you later.